Good afternoon, everybody. In today's lecture, we discuss on the topic draft tubes of Unit 4, the hydraulic turbines, Part 2. Draft tube is mandatory in reaction turbines. It's an important component in reaction turbine. The draft tube is a conical tube attached to the runner exit. So one end of this conical tube is attached to the runner exit and the other end is submerged in tail race, tail pond, downstream water. So kindly remember that for the smooth transfer of water from the exit of a reaction turbine, the draft tube is useful. Why draft tube is necessary? In any reaction turbine, the pressure at the exit of the runner is negative, that is, less than atmospheric pressure. Outside the runner is atmospheric pressure. You all know that water directly cannot discharge itself from a low pressure to high pressure. That is why you require a device for the smooth transfer of water from the turbine exit to the tail race, tail pond. So that is why this conical tube is an important device in the case of reaction turbine. It acts as recuperator of pressure energy. It passes on the water from the exit of the reaction turbine runner to the tail race. It also assists for a good maintenance of the turbine. Why? Because if you don't have draft tube, the whole runner, entire thing has to be submerged in tail race. Instead of that, if you have a draft tube, you can keep the turbine at a higher level so that the maintenance or the observations are very easy. So these are the main important things regarding the draft tube. With this background, let us go into defining what is a draft tube, what are the various types of draft tube. Then I am telling the pressure is less than atmospheric pressure, but I will show it to you also what is the pressure at the exit of the runner also. I will show it to you. And finally, what is the efficiency of a draft tube? So these points let us discuss in today's class. So today's thing is draft tube. It's a pipe of gradually increasing area. Please note down. Gradually increasing area. Area of cross section should go on increasing. That's why I told it is as a conical tube, which connects what? On one end, it is what? Which connects the exit of the runner. This is one side. The exit of the runner and tail race. So this is what you should remember. For example, if I take gradually increasing cross-sectional area, this is how it looks like. See the area of cross section, how it is. So at one end it is connected to the turbine and the other end is kept in the tail race. So this area of cross section, if you see, gradually increasing. And here it is turbine exit. And this is tail race. This is what we should understand. Next, they always one end is connected to the outlet of the turbine, the other end is always connected to the tail race. What are the purposes? Number one, first one is it transfers the water from the exit of the runner, exit of the reaction turbine runner to tail race. This is first. Next. Right. Why it is required? The pressure at the exit of the runner is negative. That is less than atmospheric pressure. Hence, water cannot be discharged directly. Water cannot be discharged as it is. We need a device, and that device is draft tube. And what are the other purposes it serves? Actually, it allows the turbine to be set above tail race so that the inspection of the turbine is easy. So this is one of the advantages. Next, last is it converts large amount of kinetic energy, large amount of kinetic energy which exists at the runner exit to the useful pressure energy. These are its purposes. There are different types of draft tubes. What are the various types of draft tubes? The various types of draft tubes are simple, number one, which is called as simple conical draft tube. This is generally what we prefer always. Then again, simple elbow. Elbow means 90 degrees bend. Elbow draft tube. And third one is Moody's MOODY. Moody's charts we heard. Moody's spreading tube. And fourth one is the elbow draft tubes. Elbow draft tubes. It is elbow draft tubes with circular opening at the entrance and rectangular or square opening at exit. Now I will show the figures. Please draw the figures along with me. So this is one simple conical. So this is axis, right? This is the inlet to the draft tube, outlet. Inlet is connected to turbine exit. Outlet is connected to tail race. So this is first one. This is what we call it as number one. And what is number two? Elbow. Elbow means what? For example, if I draw this is the entry. See 90 degrees only. So this is how the flow enters and leaves. This is entry. This is exit. Exit. So this is number two, elbow type. And third one is what I mentioned, Moody's chart. The Moody's thing will be like this. So this is how the draft tubes looks like. It permits water to flow two directions. This is the entry. This is the exit. And this is also exit. So this is type 3. This is what we call it as Moody's thing. And the axis, if you write it, this is the axis. Last one is what actually this is again circular opening at the top. And then actually if I see exit, the exit is not circular. Exit is rectangular. So this is entry, right? Entry is circular, but outside is square or this is exit. So this is fourth type. So these are the four types of draft tubes, right? Generally, if you take it, this conical and moody, so 1 and 3 are basically efficiency wise good. Efficiency wise good, right? And whereas 2 and 4 can be kept at low space. So where space restriction are there, we go for 2 and 4. Otherwise, we go for 1 and 3. Kindly remember that. Only requirement of space will be less, right? In the case of 2 and 4. So this is the next one. What is draft tube theory? The next topic is draft tube theory. In this theory, you understand what is the pressure at the exit of the runner.
So now I draw the figure. You also draw along with me. So this is the turbine exit. Just for understanding sake, I am writing like this. Then from here, actually the draft tube is there. This is how the draft tube is, right? So this is the end of the draft tube, which is kept actually in water. So this is water level. This is water level, right? This is kept. So this height, if I take it, I call it as capital H suffix S, whereas this height I will call it as Y. Understood? Right? So this I will write as 1. This I will write as 2. What is 1? 1 is inlet to the draft tube. Inlet to the draft tube. What is inlet to the draft tube? It is nothing but the exit of runner. Exit of runner of reaction turbine. What is number 2? Number 2 is the exit from the draft tube. What is it actually? It is into the tail race. So this is the first. Then what are the notations that I mentioned? What is HS? Actually, HS is nothing but it is the vertical height of draft tube above tail race level. What is Y? It is the vertical height from the bottom of draft tube, right, to tail race level. Vertical after above the tail race level up to the exit, up to the inlet. Fine. So these are the things. Now what I will do, apply the Bernoulli's equation. Applying Bernoulli's equation between section 1 and 2, between sections 1, 1 and 2, 2. So in the figure, if you see, this is 1, 1, this is 2, 2, right? If I apply it, right, that means the inlet to the draft tube to the outlet of the draft tube. So it is P1 by gamma plus V1 squared by 2G plus Z1 is equal to P2 by gamma plus V2 squared by 2G plus Z2 plus head loss in draft tube, HF. This is what I have written. Then we can also write actually this P2 by W is nothing but PA by gamma, right? PA by gamma plus Y, because if you see, this is the turbine exit. So this is how we have drawn the draft tube, right? And now this is here the tail race level. So this is Y, which we mean. So here the pressure everywhere is what pressure actually? Here the pressure is atmospheric pressure PA. So what is the pressure? P2 is equal to P2 is the pressure here P. So it is PA by gamma plus Y. That's what I have written. So if I do that, actually, again, let us go P1 by gamma plus V1 squared by 2G plus Z1 means what? Actually, the total datum head, that is nothing but HS plus Y, right, is equal to P2 by gamma means PA by gamma plus Y plus V2 squared by 2G plus what is Z2 is equal to, here only I have taken Z2 is 0 plus HF. So if I simplify this equation and put actually this, what will happen? You see, y will be cancelled. This y and on this y will be cancelled. So what will be lying? If you see, it is P1 by gamma is equal to, if I take that on the other side, PA by gamma plus y plus V2 squared by 2g plus HF minus V1 squared by 2g minus hs minus y. So plus y minus y will cancel. So P1 by gamma is equal to PA by gamma minus V1 squared by 2g minus V2 squared by 2g. Right? Right? This is the one thing. So minus hs. So what I understand from this, so this all this is a positive quantity, because if I see what is V1, this is the V1. What is V2? This is the V2. The velocity here is more, here is less. So V1 squared by 2g is more, V2 squared plus HF. So all this I have to subtract from this. Therefore, it is PA by gamma minus something, right? That means P1 by gamma is less than atmospheric pressure, less than atmospheric pressure. This is what precisely I was talking. P1 by gamma is equal to negative pressure. Where what is Py by gamma? This is nothing but at the exit of runner. So at the exit of runner, the pressure is negative. That is why we need a draft tube. And what is the final conclusion? The efficiency of draft tube. The efficiency of draft tube is equal to eta D. We will write it. Actual conversion, because what draft tube will do? A conversion. Actual conversion of kinetic energy to pressure head divided by to the kinetic head at the inlet of draft tube. And what is it actually? So that means what I can write, what is theoretical conversion? Theoretical conversion of kinetic energy is equal to V1 squared by 2g minus V2 squared by 2g. Then what is actual conversion? Actual conversion of kinetic energy is equal to V1 squared by 2g minus V2 squared by 2g minus head loss. This is it. So therefore, eta d is equal to V1 squared by 2g minus V2 squared by 2g minus HF divided by what is the initial thing, that is V1 squared by 2g. So this is the draft tube efficiency. So with this, I have completed a short note on the draft tube, a very, very, very important component of the reaction turbine. So take it and then work on this. So this is the theory question. Please work on this. With this, the part two theory part we have completed, and we will take up problems in the next two classes. One class devoted to direct Francis turbine, and one class devoted to Kaplan turbine. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.